I've always been fascinated with gyroscopes, and I think it's safe to say that I share this fascination with anyone who's actually played with them or watched demonstrations of their behavior. Like most students of physics, I can appreciate the right-hand rule and the law of conservation of angular momentum for their predictive powers, but neither of these tells me much about why this rapidly spinning wheel should behave so unexpectedly, so non-intuitively, and so mysteriously. In this video, I hope to shed some light on this mystery. So, to try to get a sense of how or why gyroscopes behave the way they do without actually using a gyroscope, we're going to instead use this device that I call a trajectory deflector in this thought experiment. And basically it consists of a structure that has 4 hollow curved tubes on it. And the way we do our thought experiment is we launch these 4 metal balls from 4 different directions into the trajectory deflector, and once the balls enter the tubes, they're deflected or diverted, and they pass through the tubes with no friction. We also assume that the trajectory deflector is perfectly stiff and there's no deflection in it, and the balls pass through and then exit. And so what we're going to do now is examine the forces on the actual balls, and then that'll allow us to determine the reactive force on the deflector and shed some light on what happens in gyroscopes. So I'm going to do 2 cases. The first case being the simple case will just give us a quick sense of how this thing works and how the vector analysis works, and then I'll move on to the more sophisticated case, which actually will shed some light, hopefully, on gyroscopes. So here we are looking at the front view of the deflector, and you can see each ball just about to enter its respective tube, and these black arrows represent the velocity or velocity vector at the point of entry. And now I'm showing the balls leaving their tubes with a new velocity vector. So in this frame now I've taken the input vector and relocated it or superimposed it at the point of exit, and this will now allow us to create the vector which represents the change in velocity for each ball. And this vector also represents the direction in which the sum of the forces acted upon each ball as it progressed through each of its tubes. And so we can take that same basic vector now and flip it around 180 degrees and locate them at the midpoint of each of the ball's trajectories, and this will now indicate the reactive force imposed upon each tube by virtue of Newton's third law. And now we can strip away everything else and look at these reactive vectors, and we can see that they all react directly through the center of the deflector assembly, so we shouldn't expect any torques. And we can also see by this circle that they're all the same magnitude, so we shouldn't expect any sum forces on the deflector. We can spin the deflector around, looking at the side view, and we can see that the forces are in the plane of the deflector, so there shouldn't be any torques in any other plane as well, as we can see from the top view. So the conclusion, no non-intuitive reactive forces upon the deflector. Okay, now the more interesting case. Now in this thought experiment we're going to begin exactly as we did in the previous experiment, but this time just after the balls enter their curved tubes, we're going to impose a torque about the x-axis as shown, and this will simulate the effects imposed by gravity on a real gyroscope if it was actually supported right at this point here. So just as the balls enter the tubes, we impose a torque and allow the balls to progress and continue to exert this torque, and then just before the balls exit we stop rotating the deflector. So let me reverse that just so you can see that again. So the balls are just getting ready to exit now. We stop the rotation about the x-axis, allow the balls to exit. So now in this frame we can see the input vectors on each ball as well as the output velocity vectors. And now we copy the input vectors at the exit location, and this allows us to derive the change in velocity vector for each ball. And this vector also represents the direction in which the sum of the forces was exerted upon each ball as it moved through its tube. And as in the previous thought experiment, we can take these vectors and flip them around 180 degrees and relocate them as shown at the midpoint of each tube, and this will now represent the reactive forces imposed on each tube. So here's a quick three-dimensional spin of the entire deflector assembly, just so that you can see how all these vectors are actually oriented. Okay, well now let's take a look at these reactive forces on the deflector and see if they might reveal something about how an actual gyroscope behaves. So we can look at the new tilted front view, that is looking down the y-axis after we've tilted the deflector about the x-axis. And the first thing that becomes obvious from this diagram is we can see now that the forces do not act down the center of the y-axis. And we can also see from these two circles that the red vectors are a little bit larger than the green vectors. These two circles illustrate that the angle of each, the green vectors and the red vectors, are slightly different. So we can imagine that the red vectors are going to create a torque in the clockwise direction, and the green vectors a torque in the counterclockwise direction. Now, whether these two torques are perfectly counteracting, I didn't go into that analysis here. But what's more interesting, I think, is if we actually go to the top view now and look down the z-axis, we can see that the green vectors are entirely out of the plane, the midplane of the deflector, and these two forces are going to create a torque in the counterclockwise direction about the z-axis, and it's this torque that would create or cause the gyroscope to precess about this point, much as we see real gyroscopes precessing. And similarly, now if we go to the side view here, we can see that these same two force vectors are going to induce a torque in the counterclockwise direction about the x-axis, and this would be the torque that prevents the gyroscope from actually falling over due to gravity. I hope this video helps clear up some of the mystery about why gyroscopes precess and why they appear to defy gravity. In essence, as the arc of each point mass on the rotating rim is deviated, it imposes a reactive force on the overall gyro, and the direction of this reactive force is a function of where the point mass is on the circumference at that given time. That is, as shown by the demo, the green deflector tubes have the greatest impact. And lastly, for the sake of clarity, I intentionally exaggerated the amount of induced tilting or rotation about the x-axis. And one might object by saying that real gyros don't move anywhere near that amount, and in fact some don't seem to move at all in the downward direction. I would reply by saying that this is actually due to what's referred to as nutation, as shown in this video, and that every gyro, in order to precess, must be doing this to some extent, even if it's barely measurable. Well, thanks for watching. I look forward to your comments.